In today's video, I will cover sequential logics. Consists of 1-bit register chip, 1-word register chip, 8-word RAM chip, and a program counter. So, first question: why do we need a sequential logic? Let's think about a circuit like this. We got so to think. Let's have it thicker. We have a lamp which is powered by a battery. Here we have a switch which is a push button switch. Okay, push button switch. Whenever you push this button, the lamp will turn on. So light. However, when you release your finger, the light will turn off again. So if we have this is what we have seen before, the combinational logic. It is equivalent to let's think about an OR gate. It has two input, A and B, out. If you apply a high logic 1 to one of its input, the output will be 1 as well. However, if you remove the input, the output will immediately goes off. So, like this example, you don't want to keep your finger on the button to keep the light on. So you would need a stateful circuit. A similar circuit, we have a lamp and a power. This time we will have a stateful switch. Let's draw it like this: stateful switch. You can toggle it between two stable states, on and off. So how can we implement a stateful circuit with this OR gate? Let's think about this arrangement. An OR gate, which has one of its input is feedback from the output. Let's draw the truth table of the OR gate. Who remember the truth table? Here we have a B faded by the odd. Okay, 0, 0, 0, 1, 1, 0, and 1, 1. For an OR gate, the odd is whenever there's at least one input is 1, the output will be 1. So let's think about this circuit. Initially, we got both input 0, so the output is 0. However, if we pull the input A to 1, it will be this case. The output becomes 1, and the output 1 is faded back to the input B. So input B are not 0 anymore. When we release the input 1, it becomes 0. However, it falls to this case. The input of A is 0, but B is faded by the previous odd. It stays at 1. The output is still 1. There is a problem. You can see regardless of the input A, what value is it? It stucks in those two states. Regardless A is 0 or 1, it always output 1. This is stateful, but it can only transfer from 0 state to 1 state. So to solve this problem, clever scientists developed a structure called a latch. So what is a latch? What is a latch? Here is an example of the latch on my storage room. You can see currently the latch is on its closed state. I can have some input to pull it to the open state. Allow me to open the door of the storage room. And I can have an input to push it back to the closed state. As you can see, it stays at its closed state. So this is an bistable structure. We can implement the latch with two NAND gates. Here is our input A, but this time we call it R. And the input B, we call it S. R stands for reset, and S stands for set. And we do like this. Pull the output of the first NAND and fade it back to the input of the second NAND gate. We also pull the output of the second NAND gate and fade it back to the input of the first NAND gate. So this is a cross-coupled structure. Let's call this Q and call this Q bar. Who remember the truth table of a NAND gate? A. We are considering a single NAND gate. One. Okay, a NAND gate is which means not AND. So we have a 1 0 0 0. Let's see what happens of a cross-coupled NAND gate. Because it is a cross-coupled, it requires an initial condition, which is randomly assigned during power up. Let's use a red pen to represent a logic 1, and use a blue pen to represent make it thicker. Logic 0. I will copy this drawing for several times to ease the explanation. Firstly, let's assume PQ is 1 initially. Let's assume the Q is initially logic 1 and the feedback to the second NAND gate is also 1. Let's also assume Q bar is logic 0. Similarly, feedback to the input of the first NAND gate. We also assume R is logic 0 at this moment. Let's see whether this latch is at its stable state. See here, if both input are zeros, the output is 1. Yeah, there's no contradiction. Also say this NAND gate. If input A is 1 and the input B is 0, the output is 0. So here, the NAND gate is at its stable state. Okay, let's see how can we reset this latch down here. We copy this output value to the second drawing. This time, we pull the reset pin high. And see this condition. First input is high, and the second input is low. It is this condition. The output becomes 0. Let's color it in blue. And say this, at the second NAND gate, both inputs are zeros. The output is 1. So in this case, if we pull the reset pin high, we can toggle the state and make the Q output change from logic 1 to logic 0. Similarly, let's first copy the state down here. If we maintain the reset pin as low, and the feedback from the second output, the Q bar, is high, and the feedback from the Q is low. Let's pull the set pin up now. Let's move the truth table down. Okay, now the reset pin is low and the feedback is high. Low, high. The output is 0. No problem. No problem. Say if the set pin is high and the feedback is low, it is this case. The output becomes 0. And the feedback to the input of the first NAND gate. 0, 0, 1. Okay, that's how we can switch the latch between its two stable states by pulling reset and set pin up and down. A latch is an elementary part which keeps the state. We can see the gate level implementation of flip-flop. Let's find the implementation of a flip-flop. Only use NAND gate. This is the case. You can see the heart of a flip-flop is a SR's latch we have just analyzed. So what is a flip-flop? Let's search some photo of flip-flop. Okay, flip-flop is a kind of flip-flop logic, digital. Anyway, let's draw it. A flip-flop is a digital logic digital component. It has a clock input, a data input, and two outputs, Q and Q bar. We also get a reset pin. The data pin is an input, and the Q pin is the output. Q bar is also an output, but it is an inverse output. In a normal case, the inverse output Q bar is always the complement of the output Q. We have a reset pin. As we analyzed earlier, when power up, the state of Q and Q bar are randomly assigned. A reset pin just act as this reset. It put the state of the flip-flop at a known state, which is Q equals 0 and Q bar equals 1. The basic operation of a flip-flop, let's say D stands for data, the input. D is somehow keep 0 at the first clock and becomes 1 at second clock and keep going. we have a clock pin. It clock pin. It rests at the middle of the second clock. What happens to the Q? Q will stay at low until the resting edge of the clock. It copies the state as a data pin and copy it to the Q. As we said before, Q bar is the inverse output, so Q bar will be high at some moment, drops. At the moment that the clock rests, it copies the D and do an inversion. And later, the D drops. At this moment, the Q won't drop at this moment because the clock isn't transferred from low to high. Let's think about this. If the clock transferred from high to low, what happens? The Q will stay high because the flip-flop only change state, only copy the data pin to the Q pin when clock transfer from low to high. Doesn't matter the clock is dropping. Okay, now the clock is encountered another resting edge. Here we copy the state of data pin to the Q pin. The Q drops and the Q bar rests. That's the basic operation of a D flip-flop. Because the D flip-flop is an inbuilt function of the Nand2Tetris, we don't need to implement this D flip-flop. As you can see in the Nand2Tetris tool, the built-in chips, DFF is here. Data flip-flop. It has an input and output. Of course, I mentioned there are 5 inputs, 5 ports, data, Q, reset, and Q bar. Also the clock. In our Nand2Tetris language, we have omitted the reset, the clock, and the inverse output. You can assume all elements in Nand2Tetris are commonly connected to the same clock. If you are doing a language like a Verilog or VHDL, they are both productive HDL. You can connect different clock signals to each of the chip. But in Nand2Tetris, we assume the clock pin for each chip are commonly connected, and we don't need to specify which signal is driving the clock pin. The D flip-flop in Nand2Tetris can be simplified to this form. D, let's see, what's a port's name. Okay, here, in and out, that's simple. Still, the out is copied from in at a clock resting edge. Okay, let's move on to the, I think it's 1-bit what is called bit register. A flip-flop by its own cannot store information long, because whenever the clock rises, it copies in to the out. It can only maintain the data for one whole clock cycle. So what happens if we want to keep the flip-flop to keep the state for a longer time? We will have to use this structure. A flip-flop have a master output, but at the same time we pull the output back to its input. However, here is a problem. Let's say at this moment, the data is changed from high to low, while the Q, the output is still high. There will be a contradiction. It will be like a short circuit in analog system. So we cannot directly pull the output and fix it into the input. We will need a max. Let's erase this. We will need a max and put it back, A and B. A is in, and there will be a signal called load. If the load is low, the output will be feedback, will be copied back into the input of the flip-flop, so it keeps the previous state. Otherwise, if the load is 1, it takes new value of data. Let's call this this signal feedback. Okay, let's start coding. I need to download this practice 3 file. Okay, open up this practice 3. Go to computer systems and extract this practice 3 here. Go to practice 3 and find, am I recording? Yeah. And find part 1, 1 bit. Okay, let's code in the diagram I have just drawn. We will have a max, which has A is connected to the feedback signal, lowercase f, and the B pin is connected to the input signal. We got the selection, SEL, connected to the load signal. And finally, we got our master output, as well as the feedback signal need to put back to the, sorry, not here. I need to name this the output of the max, call it input to the DFF. The output is in DFF. Okay, we will have a DFF next. The input is input to DFF, and the output is our master output, as well as a feedback signal. Okay, let's try if this works. Hardware simulator. You don't need I have figured out. You don't need to load chip every time. You just load the test script. Prac 3 part 1 and the bit.test. When the execution reaches this load bit.hdl, it will automatically load the corresponding HDL. Let's try this. See, loaded. Run to the bottom. You can drag this speed control to speed it up. Quite a long test. Yeah, you can say successfully. It means my implementation of the bit is correct. Next, let's move on to the one-word register. Is there a detailed description? How can I do this? I remember there's a description in the HDL file. Okay, here it is. If the load t equals 1, then output t plus 1 equals in. That's what the 1 bit does. The in and out will be 16 bits. So that's 16 bits in parallel. Okay, let's do this. Bit. What's the structure of bit? In, load, out. In equals in. No, the zeros pin of the in. There's only one master load signal, so we put a load here. The output will be connected to the master out. Zeros pin of the master output. Let's do the trick I have introduced in my fourth video. Online, find some language you are confident. This time I use a online C compiler. Just some language you are confident. Let's replace this with what I want. /n means change line, and I will put two numbers I and I. In order to make those I change, I would like to have a for loop. I start from 0. I need to specify the I to declare the I. Int I equals 0. I less than 16 pins in total, and I increment. Okay, let's see what's missing. Try it. Oh, must be something missing. Replace those zeros with D, percentage D, so it can receive the value from those parameters. Copy the generated text and paste E. Why not? Copy. Paste. Oh, what's yeah. Align it. 0, 1, 2, 3, 4, 5 down to 15. Yeah, this should work. Let's go back to our hardware simulator. Load the test script for the register. Fast forward. Go. Cool. That's our implementation of the 16-bit register. So what's next will be 8-word RAM chip. In a 8-word RAM chip, you will have 8 registers in parallel, and each register have 8 bits. How many do I have? 7. Okay, plus 1. Okay. You will have 8 of them in parallel. So how can we select? Let's open up the HDL file for the RAM 8. Okay, 8 registers. It register in parallel. You would need to use address to address each of them. What you may think is to have a DMAX D6 8-way 16 and connect the output of this DMAX is 8-way 16 to each of the register, and at the end to have a max 8-way 16 to receive the output from each register and to produce our master output. And both of those max and DMAX are controlled by address. So let's see, in the tools folder, do we have a DMAX 8-way 16? In this folder, Nand2Tetris tool built-in chips are resources you can use in this project. DMAX 8-way but no keyword 16. You can see the input and outputs are single 1 bit. There is no chip called DMAX 8-way 16, so we cannot have this structure. Let's see, do we have a MAX 8-way 16? Yeah, MAX 8-way 16. So what can we do? Instead, we can remove this 16-bit DMAX 8-way and have all the input commonly connected to each register. Do you remember there's a signal called load for each register? Here it is. So we can have a single input and utilize this DMAX 8-way. Single input DMAX 8-way. And connect each of the output to the load signal of those registers. Controlled by address signal. I believe it's 3 ways because 2 to the power of 3 equals 8. To address to each of the 8 registers. We can still use MAX 8-way 16 because it is here. So let's implement this. Let's open up this RAM 8. RAM stands for random access because you can randomly pick up which address to access using the address signal. First, let's have 8 registers. Register, remember what is a signal that the register take? Register take in, load, and out. In equals in because we assume the input signal is commonly connected to one common point, and the load is splitted from one DMAX 8-way. Let's name this the first load signal as load 0. Load to the zeros register. Load 0. The output is to a DMAX. So let's call the out as out 0. So output from zeros register. Okay, we do the same trick as before. Use our online C compiler. This time replace this expression. Hold 0. Here we got a %d. D stands for decimal. %d. And I E from 0 to 16. This should work. In, load, out. Okay. Right. Go back to our code. Paste it here. Do an indent. Let's double check. Oh, too much, because we only need 8 registers. Okay, 0 to 7, that's 8 registers. Here we call it what register? Back. And we will implement this dmax 8-way. Call it load addressing. Dmax 8-way. Let's see what's the input and output of the dmax 8-way. Would be like this. In select and A to H, 8 outputs. Paste it here. Okay, what is in? It's a load signal. And what is select? That's a 3-bit address. What is A? A would be load 0. B is load 1. C is load 2. D is load 3. E is load 4. F is load 5. G is load 6. And H is load 7. Now we have finished the load addressing logic. We will have to implement this output aggregation logic. Aggregation. How to spell aggregation? Never mind. Just call it output logic. We have max 8-way 16. Let's check what's the input output convention of the max 16. Max 8-way 16. 8 inputs and 1 output. Let's remove those 16s. Also remove this selector because we are putting 3-bit signal to 3-bit signal. The length can be omitted. A is output 0. B is output 1. C is output 3. D 4. E 0 1 2 2 3, 4, F5, G6, 7H. Selection is address. Output is our master output, 16 bits master output. Okay, let's see what happens. Load this RAM8 test script full speed and go. Oh no, it fails at 31. Expect a load signal. Load signal. Okay, here's an additional semicolon. Load signal. Should be that additional semicolon is false. Oh, 31. 31, what happens? Address. Hey, load 0 B C L. Okay. Here's the problem. LAOD. LOAD. Replace all. Okay, also remove this. Try again. Okay, pass the test. So our RAM8 implementation is correct. What's next? Next would be a counter, which is a program counter. So what is a program counter? Let's open the HDL file and have a look. (16-bit) counter with load and reset control bits. Let's have some additional knowledge. So what is a program counter? No. Let's open up IDA. IDA is a decompile tool which can analyze a executable file. Let's try this. Randomly open up an executable file and see what happens. As you can see, every computer executable are composed with this assembly codes. It will run start from the main function, which is a main flag. Let's see, where's the main flag? Oh, this is quite a complex executable. Yeah, here is our main function. The execution will start from here, and depends on the information provided, it will jump to different subroutines, basically different functions. Let's go back to our main function, where it is. Should be at the very top. Not easy to find out. And the next. So where is this? So first line of code would be this, LEA. You don't need to understand what is it. It's just some x86 executable for Windows. So can I put a breakpoint? Yes. And run this executable and see what happens. So the execution stops at the very beginning of the main function. It is the current memory address. It is fetching 4018D0, which is here. Here is our program counter. If we go to the next step, let's go one single step by pressing F8 key. F8. It will fetch the next instruction one by one. When it encounters this GZ, it will compare this variable. If it is 0, it will jump to some function. GZ, not 0. No, GZ is this green line. Let's watch this program counter. Okay, it's not 0, so it jumps here. It will keep executing and do another jump. As you can see, if there's no jump, the program counter will increment. I think that's by 8. Increment by 8 each time. However, if it encountered a jump instruction, it will load a new value. Yeah, that's what basically a program counter PC does. Let's close this without saving. Okay, open up our whiteboard and some space. Is there enough space? No. Let's do a new whiteboard. A program counter which basically takes 3 control signals. Reset, load, and increment. Too small. Okay, following those rules, you can say if, else if, and else. An if-else statement has a priority. Whenever it appears first, this control signal will be closer to the counter itself. Let's first draw a counter, which is 16-bit. See, the input and output are 16, so it's a 16-bit counter. Has a output. Let's call this signal in counter. Whenever the condition appears first, it is closer to the counter because it override the resting control signal. Whenever it executes if statement, if then statement, here's then. It will jump to the end without considering any of those signals anymore. Whenever you see a control signal, you will have a max. Max have A and B. This signal is called a reset. So when reset is 1, the output which is here. Ink C is the input to the counter and will be copied to the output at the next t+1 time. So B will be false. False means 16-bit 0. It puts reset the counter. Let's see what's the next condition. It's a load. What load does? Load. If a load is 1, it takes a new input. So the new input will appear at port B, because when the control signal is 1, it takes the value of B. And see what A does. A is let's keep doing. There's nothing, and the A should be the else signal. Else, let's keep doing the next if then. If ink is 1, the output equals output +1. So what this does? Another max, which is controlled by ink. When ink is 1, output t+1 equals output +1. So there will be a ink 16-bit down here. Otherwise, ink should do this. Otherwise, it's directly a feedback. Direct feedback. What does this do? Okay, input is here connected to the load. So this signal is put through the A. Reset load ink, and the default will be feedback. So let's rename them. Feedback. Call this ink out. Call this signal load in. Load in. Load. Not load. Load not, and call this reset not. Ink C. Okay, let's implement our PC program counter. Let's start from this ink 16. Do we have a ink 16 in the built-in folder? Ink 16. In and out, yes, ink 16. Ink 16. in equals a signal called feedback. And out equals ink out. Let's have our this max 16. A equals feedback. B equals ink out. The SEL control signal is called ink. Spelled right here, ink. And the output is called load not. Okay, that's it. Call this ink. Next layer would be load control. Copy this. Mark 16. A is load not. B is new input. SEL is load. And out is called reset not. Load not. Load out. Anyway, just a name. Let's check the connection. Okay. Copy this again. This will be our reset logic. B is false. Select is a reset. Out is ink C. Finally, we will have our 16-bit counter. Which is a register. Let's see what's the register's input-output convention. It has a in, load, which we are using this max to control the load. We will make this load to be always true. We are using a separate max to control the load, so we don't need to use a max inside the bit to do the load. Output is our master out. Input is ink C, in C. In C, not ink C. In C, load true, out. We will need a feedback signal called feedback as well. Connect to our out pin of the 16-bit counter. Yeah, that's it. Let's see and run our hardware simulator to see how it's going with our implementation. Counter. Fast. As fast as possible. Yeah, looks good. So that's it. My today's video. Please continue to work on your implementation for 64 word RAM chip down to 16 kilo word RAM chip. Thanks for watching. If you like my video, please subscribe and thumb up.